Hey, good morning, guys. We have 1 minute to start our lecture. I might as well just go ahead and start. And first thing in the business is that I want to talk about the correction about the notes we had from lecture 5, previous lecture. And there's a mistake made on the clear cover. And I believe several students, either Kyle or Louis or somebody else pointed out during the last lecture. So just want to make a quick correction here. So first of all, let me share my screen so you can see that. Okay, so here we go. Alrighty, okay. So last lecture we talked about several things. First of all, we talk about how we determine the sections, right? How we determine the sections. And the way we determine section is that we have determined by the width of the member that's supporting the beams and all that, right? For the height, we have to decide the height based on the deflection control. That is, the section height has to be proportional to the span length, okay? So that's what we talk about. And then we went into the detailing, right? The bar spacing and all that. So we talk about the terminologies of the spacings. We talk about how we determine the spacings, so on and so forth. And there's a mistake made during the last lectures, is that when we talk about the bending radius 2ds, I mistakenly labeled that from the center of the bending radius to the outside edge of the steroids. That was wrong. Okay, the correct uh, definition of the bending radius should be from the center of the bending for the stirrups to the inside edge of the stirrups. All right, to the inside edge of the stirrups. Now, I believe I have corrected them in the lecture notes posted on Canvas, but if you haven't noticed or you haven't corrected on your own notes, please do so, okay? Now, the reason behind that is we follow the calculation, and there again, the spacing S hat is 2ds minus half of dB. So that ds is out of the equation. Then this is another correction that you just eliminate whatever was here from the previous lecture, okay? And again, this has been corrected on the Canvas. If you haven't corrected on your own personal notes, please do so. Now, following the calculation, then extra ds is gone here in the equation, and then you finally get 9.75 inch. And please double check the number again. Please follow through this corrected procedure just for your own understanding, okay? And reach a good number, okay? Reach a good number, all right? Okay, so this is about the correction from the last lecture note, okay? And again, I want to take just a few minutes talk about the homework, okay? Just a few minutes talk about homework. So first of all, let me go to lecture 6. I made some of the comments on the past homework, homework number 1, that is. So either I comment on no process on your homework, or I comment there's a sign errors, and if you want to learn more, please stay behind. And I also comment somewhere say poor write-up. So if you see all these comments, and if I wrote, please stay behind after Monday lecture, please try to stay behind after today's lecture. We talk about them in detail. But some of the general observations I have, and I want us to be more detail oriented, is that first of all, I see people writing this, right? This is definitely an interesting approach. Is that I gave you the homework PDF form, right? So the problem number 1, yada yada yada, and then there's a drawing. For example, here just put some distribute loading, ask you to do a diagram, and problem number 2, okay, yada yada yada. I have a cantilever beam, for example, and problem number 3, I talk about what is grade 6D, what is a compression test, and so on and so forth. And some of you guys feel like there are a vast space on the A4 page, so you just goes in and talk about problem number 1. I draw a smaller even drawing and give you some diagram, and here and here, and write a bunch of words, and look, check, I have the answers. And for cantilever beam, some of you also did the same thing. So to do this and sort of did that. And for the grading, you just 60 and write a bunch of words, which is pretty light and very hard to see after scanning. Okay, so this format is not encouraged. Okay, there are 2 reasons behind it. One is that it's just not easy to follow through what you're doing, and I cannot seem to find what I needed from the answers. Okay, so your correct answer might be buried inside, so I cannot find it. Second of all, notice on some of the scan pages, right? It's so small. It's so small, so I cannot see them. Hence, I cannot find the correct answers. So If you have the comments like this saying this is not the right approach, please redo it. Okay, so what is the correct format? Correct format is that please just use whatever I give you as a cover page, right? It's any project you do, right? So it's like a cover page. You simply just have to copy paste it or as a first page of your homework. So this is more like a page 1, right? So next page, right? So you do either you use iPad or you use like a pencil on the paper, scan it, doesn't matter. So you say problem 1, okay, and you say solve like I do in a course, or use other word, but just remind me, look, I'm starting solving it, right? So use your equations, right? Equilibrium, for example, sum of the moment, and when you draw shear diagram, moment diagram, label them clearly, give me the number, right? Say this is 100 kips, 200 kips, right? Now, if you want to be more delicate, that's why when you use engineering paper, you can draw the scale up to scale, right? So this is, for example, shear force, and so on and so forth, okay? And provide a reason like this, right? Organize the way. This is problem number 1, yada, yada, yada. Then problem number 2, right? And so on and so forth, so on and so forth. Okay. Now, why I say there's no process? What I mean by that is I want to see, for example, if you want to do the shear diagram, you must do some linear interpolation, right? Say this is the distance like x1, this is x2. I want to show, like, I want you to show me that how you get this value here. For example, x1 divided by v1 equals x2 divided by v2. I use similar triangle, which this case is not, but you use the detail to do the calculation. So I want to see them, right? So you may ask question, Bob, why bother? I gave you a clean sheet already. Well, I like to interact with you. I want to see the process, know how you think, and it'll be easier for me to point out the mistakes. Now, some of you did reverse way. Before submitting, call me up and trying to ask me to verify your answer. Sorry, gentlemen and ladies, I cannot do that. But I can do is that you provide your detail in the homework. I can comment and make corrections. And I wouldn't worry about grade too much as long as you put your effort in and the mistake is not horrible, you won't get any bad grades on it. Okay, so homework is more a way of us communicating at the thought level. All right, so please treat it seriously and in a very present it in a very organized and clean manners. Okay, so that's about the bad process. Okay, so I want all of you who has a remark saying stay behind, do stay behind. We can talk about in detail, but that's just the general comments on homework number 1. Okay, so quickly on homework number 2, I wrote another email last night saying that if you haven't got any stress, strain, and internal forces on the homework, please do so and resubmit before Thursday. And I want to pause. There's a question. Will you eventually post solutions to the homework? I'm sorry, Thomas, I won't. But if you have a question, you can come to me. And this specific error after grading, you can always come to me. Okay. Thank you very much. And then coming back to homework number 2. All right. Now I only have one problem with homework number 2. I like a lot of you guys use tables and know that for different cases. For example, use case 1, case 2. You have a nice table. Show me what's what. Compression force, tension force, maybe for example strains, and know that. That's nice. I like that. But bear in mind that we are dealing with physical problems, actual physical problem. That means if you have a section, right, at least I want to show one drawing per problem. I want to see one drawing per problem at least, that you show me the strain diagram, right?
Do you want it per case?
No, I don't want per case because that's too
Okay,
much,
so
right?
you'd want one for like problem 1, problem 2, and
Yeah,
problem 3, because I
yeah,
didn't do one for problem 3, and
that's okay.
that's what
That's okay. Yeah.
I
So
got a message saying to put them for each problem. So
yes, exactly. So I didn't grade any of your homework number 2 yet because it's a problem. So if you just miss one, quickly add it up. They won't cause any grade deduction. I just want us to be uniform in terms of format. Is that okay? Clear? All right.
yeah, so
Okay.
just I gotta go back and do that thing for number 3, I guess.
Right. You just need to add it. I mean, if you already have all the things there, if you have empty space, just add it there. It won't be a big deal. You know what I mean?
So, I just got a question on that on the homework. Like, I didn't have any of the drawings.
Sergio, let me finish what I'm talking right now and we can get back to your question. Is that okay?
Yeah, that's good. Sorry
All
about
right.
that.
No worries. Thanks. I just don't want to lose my train of thought. Okay. Thank you so much. So let me just quickly finish this. So the reason or the fact that I want us to have at least one set of this strain, stress, that is, okay, this is the Winnie stress block. This is the tension side of it. And this is sorry, this is actually not the Okay, so tension side of it, Fs, and I also want you to show like compression force. You don't have to label them exactly, but at least I will see that what you understand is this is the internal forces, okay, and this is the stress. All right. Now, some of you did very nicely. Okay. I see that even for different cases, some of you might show me a series of drawings of case 1, 2, all the way to 10. I don't force you to do that, but this is what I like because this way you can really see what is happening as your strain getting increased or decreased. Okay, so for all the problem 1, 2, 3, 4, if anywhere the analysis is involved, either singly reinforced, doubly reinforced, for now it should be singly reinforced more. I just want to see one set. You don't have to do them all, right? For all the cases, at least per problem, I want to see a set. Two, you form a habit. Whenever you go, even in a design office, when you pull out your pencil and actually do the design, I want to see a one set. The reason are two. One is that not only you can monitor the strain, but you can also monitor the compressive zone. And the compressive zone is very critical. Compressive zone is very critical. Sometimes you may end up very small compressive zone that is within the concrete cover, and that will not do. That will not do. All right. So let's get back to the questions. Emily, are you set on the third adding drawing to the problem? Are you okay?
Yeah.
Okay, good. Now, Sergio, can we get back to your question, please?
Yeah, my question was like, I got a comment, just draw the strain, stress, and internal force diagram.
Oh, sorry. Can you unmute yourself, Sergio?
Yeah, sorry.
Yeah, sorry about that. Go ahead.
Uh,
Hmm.
so I got the comments of strain. You need to draw strain, stress, and internal force diagram. But then I also noted that I got 11 points in the homework. So I was wondering if I really messed up the homework, or it's just because I
No,
didn't.
homework number 2 was not graded. If you got tens because I just put something there, meaning I have seen it, you need to rework on it by adding this diagram to each problem, and I'll regrade it by Thursday.
Oh, okay,
Yeah.
perfect.
Did
Thank
you
you.
read that email? I sent out an email last night.
Yeah, I sent that email.
Okay.
And I needed to redraw it, but I didn't know if I also messed it up something else.
No, I don't think so. I haven't graded anything yet. So just add that drawing to your problem. If you already solved it and you think your answers are right, that's okay. You don't have to rewrite the whole thing. Just add
Okay,
the figures for each problem. Is that okay?
okay, sounds
All
good.
right. No problem. Anything else? I see Zach has a problem. Zach?
Yeah, Professor. So I think some questions a lot of us are having right now
Uh-huh.
is if we can't like check with you prior to submitting homework to know because like you didn't say in the problem, how we had to write everything and the different like ways that you wanted it presented. And then if we can't check with you, and if you also don't release your answers afterwards so that we can compare and see where we went wrong and things like that, um, how are we supposed to know everything that you're looking for? And
Zach, that's a very good question. So my answer to this, first of all, let me differentiate. You can check with me on the approach, meaning you can check with me, say, if this is the correct approach, and I can tell you whether it is or it is not. And that does not mean you can ask me, say, Professor, does this answer sound good to you, sound right to you? All right, so there's a differentiation of that. Second, Zach, I think the best way to answer your question is that if you watch the recorded lectures closely, if you follow the way I solve the problem, I always have a chart like this, okay? Although it may not be complete, but at least I will show the strain diagram in my solutions, where I assume you guys will do the same. And if you remember, almost every lecture, I emphasize, if you draw this drawing without even doing anything, I give you 20% partial credit, and I emphasize that.
yes, sir. And I that in particular, yes. Like you've mentioned that several times. And then I think if homework is meant for us to try and learn, what's the reasoning for not releasing your solutions so that we can try and learn and have something else to kind of prepare ourselves so we know exactly what's being asked for from each question when it comes time for test time? Because our
Zach,
solutions, I think, would benefit
Zach,
greatly.
Zach, that's a good question, and let me quickly answer that. Normally, when I grade the homework, if I grade it, I will tell you if you made a mistake in the calculations or not, and you will know immediately if you made errors or there or not. You can check quickly. And if you made a horrible mistake in terms of selecting the wrong approach, and I will actually label out for you. So I think that's very detailed. And I personally grading the first couple set of homework without grader. So if you have any question, you can come to me. That's A. Two, the reason why we're not posting homework solutions that we've been doing that in the past several years now in the department. And the majority consensus, and this is not only from us, but from a lot of students, that we see stash of the homework that have been posted. And then people just use that to come up with copies and these other things with it. And we don't like that. All right. So last to your question, if you follow the homework, if you do the homework correctly, and I can see a lot of us are doing that correctly, and you follow the review sessions and giving the problem, you can solve it. And also can review the lecture notes where we do have the correct solutions. And in the textbook, they also have the answer to the correct solutions in examples and behind the problems. And you will not, and I don't think you are, lacking of any practice problems. All right. So Zach, we are not going to post solutions, and this is not my own decision. This is more collectively decided together from past semesters. So sorry, that answer is no. Okay.
Yes, sir. Thank you.
No problem. Anything else, ladies and gentlemen, on the homework? Okay. I spent quite some time on the homework because this is critical. And like I said, I think this is the best way to practice yourself. And if you have any questions, I welcome any email. Like I said, I do not like to check your numerical answers, but do like to interact with you. So I encourage you and strongly encourage you to email me if you have any question about the homework. And those of the students, 4 or 5, have emailed me, all got answers instantly. So I'm very quick in terms of answer emails. All right. Okay, any questions on the homework? Are we good on that? All right, again, for those of you I mentioned stay behind, please do. So let's continue, okay? All right, so let me draw the line here, and today lecture 6. All righty, so what we're gonna do for lecture 6, right? So first of all, we can talk about design of singly reinforced section, okay? Design of singly reinforced section. But before we do that, okay, I want us to have a quick review of what we have learned so far, right? So first thing that we will have a section, and for example, if a single reinforced is going to be looking like this, okay, so this is singly reinforced. Okay, and the step is that first, when you do analysis, that is first assume yield. Okay, that means the bar has yielded already. Okay, and that gives you an idea. Strain in the steel epsilon s is bigger or equal than the yield strain epsilon y, and we assume that. Okay, and from there we can use the T tension equal to ASFY, which is the total tension force of the bar. Okay, and then to get the compressive zone, right? And then to check the Mn equal to T D minus FA, and to check the strain, the last layer of the bars, and to check stress reduction factor phi. Okay, so that is, we use different number, Roman number 1. So that is for a singular reinforced case. Not bad, right? Now for doubly reinforced case, okay, and again, this is analysis, and this is a quick review of what we have done so far. Okay, analysis. All right, what's different is that we provide compressive bars on the top, right? So compressive bars on the top, just to show the difference, right? Show the difference. Here, just a single layer on the bottom here, multiple layers, different story. So that's for the compressive reinforcement, right? So the step is first assume yield. Always assume yield. Why is that? Because we need a starting point. And the starting point is that assume yield in the tension, so epsilon F, epsilon S bigger than epsilon Y, so on and so forth. And then also we have to make sure the compressive reinforcement, strain in the compressive reinforcement, epsilon S prime, is not yielding. Okay. Some of you may say, what if it yielded? Then we use the yield strength of the stress for the stress in the compressive reinforcement. Okay. Next step is again epsilon S bigger than sorry, get this clear. Epsilon Y, yeah, epsilon Y, and then move on to get my compressive zone C by giving beta 1 A, beta 1 C, give you A, and then use that to get my compression force from the steel, which is AS prime, FS prime, and Fs prime, that is compressive stress in the steel, equal to Young's modulus of steel multiplied by epsilon S prime. Okay. Yes, sir. Anything, Tyler? Okay. So compression from the concrete CC equal to 0.85 F prime C. Okay. And B, that's the width, and A equal to beta 1 C. Okay. And minus 0.85 F prime C and AS prime. Okay. So that is equal to the compression 0.85 F prime C bracket inside BA minus AS prime. Okay, and the tension T naturally equal to AS of Y. All right, and we strive to find CS compression from steel plus CC compression from concrete equal to the total tension force, and then reversely to find actual compressive zone A. And the reason of that is to find actual compressive zone C to double check the strain in the steel and make sure they yield. If not, we have to account for a strength reduction factor phi, and then finally the moment capacity mm. Okay, so as you can see, this is all we have learned actually, not too much. In 1 minute, right, you can list these procedures, how we calculate the moment capacity for singly reinforced section, doubly reinforced section, right? So now, what is designing? What is designing? So design in the first sense is that we give you the selection of section is given. That means you do not have to worry about geometry anymore. So for design, normally the section is determined. And in reality, it is, because we can always pick a section by experience and by the confine of the structure dimensions. So the real design, right? The real design. So if you say this is design, the geometry is set, what we're designing for. The real design is designed for reinforcement area AS, okay, AS, and then also for spacing, for bar detailing. That's what we're designing for. How many bars we're going to put in a section, and what's the spacing we provide for the bars. Okay, so how do we come up, right? How do we come up the number for, or the area for the steel, right? So what we do, first thing is we assume yielded ASFY equal to the tension force. Okay, we bring into that equation that CC, concrete compression, equal to 0.85 F prime C, B, beta 1, C, or this is A. Okay, and then we let tension equal to compression, and we find ASFY, sorry, this is step 3, ASFY equal to 0.85 F prime C, A, B, okay, and then we just say AS, right, is bigger than 0.85 F prime C, A, B divided by Fy, divided by Fy. Okay, so this is what we do. This is what we do. But you can see that this is almost like chicken and egg, right? This is almost chicken and egg. Where the A coming from the first. So to do this, right, we have to add another step, which is very critical. That is, we already know mu equal to phi mm, and assume phi equal to 0.9 to start with. So mn equal to t d minus half a, that is equal to mu divided by phi. So here we get the tension at A from the assumption. Okay, all right, so this is the gist of the design. And don't worry, we'll go through them by details. Go through them by details. All right, so now let's take a look at it by step, right? So objective of lecture 6 today, right, is to know how to design. Let me quickly remove that. How to design, okay, a reinforcement area AS, okay, with given section. All right, and we are constraining ourselves for singly reinforced section only. Singly reinforced section only. Now, before we do that, okay, we think about it. We know the section geometry already, and we want to know the bars. And the problem is we don't know how many bars we're going to have in the section. So it's very hard to determine the depth of the section, but we do need the depth as a geometry input first to come up with the area bars. So again, the chicken and egg question, right? Which one comes first? So what we do is we oftentimes assume or use an assumption for the effective depth. Okay, so what kind of assumption? So we say that if it's one layer of reinforcement provided, if it's one layer reinforcement provided, okay, the effective depth D here, or sort of we call it ds, right, would roughly equal to, and this is approximate, right, equal to h minus 2.5 inch. And I remember some of you, I think it's Trinity, asked me a question and say, Bob, how do you know it's always 2.5 where you say the clear cover is 1.5? This is where I'm getting at. If I have a section and I have a bottom layer reinforcement right here, okay, and I assume the clear cover between the edge of the bars is 1.5 inch, okay, then I estimate roughly there's only less than 1 inch of spacing between the edge of the bar to the center of the bar. So the dB should be smaller or equal than 2 inches, right? Half of dB is smaller or equal than 1 inch. So that's where we estimate for one layer of the bars, this is roughly about 2.5 inch for one layer of bars. Okay, so dB divided by 2 less than 1 inches, right? So we're talking about any bars that has a number 11 or smaller, right? Number 11 or smaller can have a 2.5 inch. So for number 11 bars or smaller with one layer reinforcement, we can easily assume the effective depth is the height minus 2.5 inch. Okay, so that's where this one is, right? D equal to H minus 2.5. And needless to say, you all know that this is the total height of it. Okay, now for 2 layers, okay, or more, right? Usually for 2 layers or more, things are a little bit complicated. Why is that? Because I need to consider this vertical clear spacing between bars, So simply what we did is that, okay, if I have 2 layer reinforcement, assuming this is the bottom layer, all right, and I have a top layer, okay, so I already know this is about 2.5 inch. So I know the group of bars, center of the group of bars, somewhere in between first row and the second row, somewhere here. So I just say, let's add 1 more inch, right? Now the total distance would be 3.5 inch, 3.5 inch. So the depth, ds, is right here, okay? So that's for 2 layer reinforcement. All right, so why this is crucial? Because when you are not given the area of reinforcement, you need to assume effective depth to proceed the calculation. So for one layer still, if you estimate it, use 2.5 as a clear as a cover. If it's 2 layer, use 3.5. You may ask, Bob, I start with one layer, end up with 2 layer. What you do? You substitute as a 2 layer with the actual concrete cover to rerun the calculation. Okay. All right. So that's.
So you're saying that we just always assume 2.5 and 3.5 respectively?
To start with, yes. When you don't know
Okay.
the reinforcement at all, yes.
All right. Thank you for answering.
No problem. No problem. So now the second thing, critical thing we need to remember before we start is the minimum reinforcement. Now we talk about this, and this is from stories in 1950s and 60s. The airplane hangar cracking, we need to provide at least larger of the 2 equations, right? What are the 2 equations? One is 3 square root of f prime c divided by fy, bwd. And remember, we talked about this bw here is the web width. Okay. Now, if it's t, that's the web. If it's I, the bw is the web. And if it's rectangular, then you're in luck. It is just the width of itself. Okay. Or it's another equation is 200 bwd divided by fy, whichever is larger, okay? Whichever is larger. So I need provide at least AS provided least of AS mean. Okay, that's a given. So even if you don't do anything, I have a section, I even don't bother to put any analysis, put a minimum reinforcement in it first. Okay, that's what you do, right? So after that, we can go into the official formal design procedure. Formal design procedure. Okay, so what is the formal design procedure? So first thing is we have to make sure phi is always greater or equal to, greater than or equal to the mu, right? That is applied, all right? And mu should equal to 1.2 md dead load plus 1.6 ml. So speaking of this factor loading, I just want to digress for a second, okay? If I have a beam and I have distributed load, and I call this omega d, and I have another distributed load, for example, half span of omega L. Okay, I see people start doing U equal to 1.2 D plus 1.6 live, which is good, but then it quickly becomes U equal to 1.2 omega L multiply maybe half of span length for the homework, and then plus 1.6 omega D multiplied by total span length because it's really acting on the full span. Now, this expression is very confusing, very confusing. What you should do, again, and this is, I did not take a whole lot of points out of this unless you make a mistake in calculation. So this is just merely for your purpose, is that if you have factor loading, right, convert, so solve, say for dead load, convert the dead load into concentrated force first, right? That equal to a concentrated P dead first. I see a lot of people you did this, which is great, okay? So you say PD equal to omega D multiplied by the span length of L, right? And then for live load, you do the same. Now I have a simply supported beam. I have a half span, and this is omega L. And I say, you know what? This is roughly here, and this is PL, okay? Now with this PL equal to omega L multiplied by half L, all right, you get that number. All right. Now, followingly, you're trying to find reactions. Say this is A, this is B, and you're trying to find RA and RB. And these should be factored, right? So then you say for factored reaction. Oops, sorry. For factored reaction, you don't have to exactly follow this, but at least you have a total force symbols so you can see it clearly, okay? So for factor reaction, for example, RA should equal to 1.2, can you see it? Right now, the factors start to appear. 1.2 PD cost, right? That's the dead load cost reaction, plus 1.6 P live divided by 2, okay? So this is where you do factor because that's the factor loading is. Okay, now if you bored of this, you say, I don't want to do this. I just want to maybe add up, and this maybe convert it into at the beginning. I can just convert it at the beginning to say that I have a dead load of omega D. So here omega U half span is 1.2 omega D, and the other half span is omega U equal to 1.2 omega D plus 1.2 omega L. That is also okay. Okay, you can also do this way to start with a factor distributed load to start with. Now, either of the approach is fine, but I need to see you use this for concentrated force, and I need to see this diagram for distributed loading. All right, now this is not in anywhere close to the fixed format I wanted to see. It's more clarity, I'm sorry, more of the importance of clarity, okay? So if you have a different format, I did not take points off unless there's a calculation error, but please try to follow the logic sequence when you do your homework. All right, okay, sorry, this is digress. I'm just gonna label here digress, okay? So this is not on the main course. Sorry, so digress on homework number 1. Okay. All right, try to minimize the digress as we go. Okay. All right. So coming back, mu equal to 1.2 md plus 1.6 ml. That's the factor moment. And you know that mn now, using this equation, right? Mn has to be bigger or equal than mu divided by phi. All right. And incidentally, we know that Mn, which is the normal flexure strength, equal to ASFY. And again, this is assuming still yielded multiplied by d minus half A. And this d is ds here, don't forget, right? That has to be greater or equal than mu divided by phi. Okay, mu divided by c phi. All right, so I move forward and say AS then has to be greater or equal than mu, okay, divided by phi f, sorry, phi ASFY, I was right, Fy and ds minus half A. ds minus half A. All right, okay. So now here is our problem. Here is our problem. Why? Right now, all I know, right, from the get-go is I have a section, I have a height, I have a width, I know the applied moment mu equal to, maybe I'm just making things up, okay? 200 kip foot. This number is made up, okay? And I don't know anything else. My point or my purpose is to put some bars in it with number of unknown, area of unknown, and spacing of unknown, right? So I arrive at this equation here where it gives me the information about area of bars. But the rest of it, let me check. So mu I know, Fy I know, phi I don't know, right? So I can assume I don't know phi because I don't know the strain is still yet. So I can assume phi equal to 0.9. All right. Now ds, well, I know for a single layer it's h minus 2.5, h minus 3.5 for two layers. So 1 st, 2 st, 2 nd, right? That's what I know. Okay. Now a, I don't. Okay. So looking at this equation, right? I have one unknown bracket inside. I don't know this fellow. So I cannot calculate the required steel area, right? So that means I need to give a guess to start the whole thing. So how do I guess it? I would say now, assume at the beginning, assume ds minus half A roughly equal to a JD. Okay, roughly equal to a JD. What is JD? If you recall, we talked about from internal forces, that is compression from the concrete, tension from the steel, and the distance between them, right? It is d minus half A, which we assume is to be JD. Say, Bob, you're playing game. You substitute one equation with a symbol and you call that a solution? No. Furthermore, I say JD is approximately equal to 0.9 multiplied ds. Okay, where ds, don't forget, where ds roughly equal to h minus 2.5 for one layer of steel, and ds roughly equal to h minus 3.5 for two layer of steel. All right. Okay, so now the equation is clear. Why? Because now I recast the equation. Now AS is bigger or equal than mu, which is given, 0.9, which is the phi given or assumed, Fy, yield strength of steel given, and then multiply 0.9 ds. Okay, where ds is assumed for these two numbers. All right, so now with all these assumptions, I can guess what kind of area of steel I need to put in. Once I have that, once I give a bars, right? I put these bars in it. I have to go back, return to beginning, right? Where it begins, return to determine actual compressive zone A, and then determine what is JD and finalize my area of steel. Finalize my area of steel. Now that is very abstract. All right. Now if I haven't lost you yet, let's take a look at an example. Okay, let's take a look at an example. So specifically 6.4 example. And folks, needless to say, this is very important, right? This is what's all about design. Okay, so what kind of example? I have a simply supported beam. All right, and it's uniformly distributed load on top of it, omega u, that's already a factor. And you don't have to even know the distributed load. All you have to know is that after moment diagram calculation, I see that the maximum moment here, okay, max here, which is mu equal to 145 kip/foot. Okay, 145 kip/foot, 145. And I have a section that preconceived. Somebody told me that, design office told me that, Bob, you got to design it. And the width of that is 12-inch. Height of that is 24. Okay, and I were given concrete of F prime C equal to 4 KSI, and I were given the steel of grade 60. All right, and the question is, what is my AS, right? And what are my bar spacing? Okay, all right. So a little bit hint when we talk about spacing, right? That is, we have to make sure the width of the beam can handle the minimum beam width as we calculated from last lecture if we put the bars in. Okay, all right. So this is the problem. This is the problem. So let's solve them, right? So solve, or in design office you write design. But anyway, so first step, right? First step, I need to determine my AS and use previous equation right here. Okay, I can write AS has to be greater or equal than mu divided by phi Fy and d minus half a. Okay, and we said this is approximately equal to mu with all the assumption built in, and this is 0.9, and this is Fy, and you have another 0.9 and ds. If you were wondering what is this fellow doing here, this is essentially assume the JD. Essentially assume the JD. And now let's say I assume one layer of steel to begin with. Only one layer still going down. Then the ds would equal to h. Yes, sir. Okay.
Sorry.
No worries. So ds equal to h minus 2.5 inch, and that gives me a 21.5 inch. It's 24 minus 2.5. Okay. All right. Okay. So with this, I can start calculate. Right. Start to calculate. So as has to be bigger and greater than top is 145 kip/foot. Because I know this got to be in inch square, so I want to convert everything into psi or pound foot, right? Pound feet, pounds inch. So this is kip/foot. I have to multiply a 12-inch per foot to convert it back to inch, and I have to multiply 1,000 pound per kips to convert it back to pound. Okay, this is on the top. On the bottom here, at the bottom here, this is 0.9. Fy is 60 ksi, right? So 60 multiplied by 1,000 psi, okay? And multiply another 0.9, remember this fellow here. And ds, right? ds now is 21.5 inch. Okay, got all my numbers here. So after calculation, I say AS has to be greater or equal than 1.67 inch squared. 1.67 inch squared. All right, so now I estimated the steel. I want to find the actual compressor zone A, and A equal to ASFY divided by 0.85 F prime CB. Okay, and that is 1.67 inch squared multiply Fy, which is 60 KSI. Now remember, you see, I go back to the KSI because I have kips underneath here. So this is 0.85 multiplied by 4 KSI. You see, this unit cancel, right? So width is still 12 inches. So I got this number A equal to, after calculation, 2.46 inch. 2.46 inch. And don't forget, this is so-called the effective or actual, sorry, not actual, this is called effective compressive zone, not
Professor?
C. Yes, sir.
Why do we have to convert it back to pounds?
Well, if you don't want to do pounds, you can do kips, but you have to make sure it's all kips up and top. Sorry, bottom and top as well.
Because like I noticed, like you're multiplying it by like pounds per kips on like both numerator and denominator.
Yeah. Well, like I said,
So,
right? Like I just said, Louis, if you can work with kips on top and bottom both, that's fine. I don't object that. But for all intent and purpose, because I have inch squared, I just want to go all the way back to pound per square inches. All right.
yes, sir.
It's not mandatory. Okay. I mean, whatever way that you find is easier for you. But all I want to make sure is that your unit are consistent. Okay. Top and bottom consistent.
All
Okay.
right.
Good observation. So effective compressive zone size equal to A equal to 2.46 inch, but that's effective, okay? That's not C, all right? Don't forget. And we'll come back to find C, but I just want to remind you that, okay? Now, next step is I started with this AS, and don't forget, this is based on a lot of assumptions, right? A lot of assumptions. I got this actual compressive zone. What happens after I get this actual compressor? Remember, the JD I assumed can be evaluated now. Okay, JD I assumed can be evaluated now. Therefore, you need to check the AS again. Okay, you need to check AS again, and AS has to be greater and equal than mu divided by phi Fy, okay, d minus half A. Now you see, I don't use 0.9 ds anymore because I have the the effective compressor zone A already. So now I can bring the number. So this is 145 kip foot, okay? And now, like Louis said, I don't want to use pound anymore. I just come back to kip inches, okay? And you can do that as long as your top and bottom are in consistency, okay? So 60 KSI, okay, multiplied by now 21.5 inch minus half A. Half A is 2.46 inch divided by 2, which is 1.23, but never mind, you can get that. So the AS now, again, is 1.59 inch squared. You can see it's different now. Okay, it's no longer 1.67, right? It changes. All right, so after this quick iteration, what I can do now is I can select bars finally. I can select my reinforcement. Great. All right, there are several options. What options I have? For example, I can use number 8 bars. So option number 1, let me use A so it'll be easier. 4.1, let's say, how about number 8? And if you remember, I'm sure you forgot, but one number 8 bar is 0.79 inch squared per bar. All right. So if I were to provide 2, I were to provide 2, then as provided would equal to 2 multiply number 8, and that is 2 multiply 0.79 inch squared, and gives me a 1.58 inch squared. And this is smaller than the required, which is 1.59 by a hair, but it's smaller, so no good. You say, Bob, 2. How about 3? Well, I can go 3, but remind us that the width of the beam is 12 inch, which is a foot. And the bar is number 8 is 1 inch. So that's quite big bars for such a small width. So I kind of already know by my experience, this will not fit if I provide 3 bars. All right, kind of already know. And I say, you know what? I'm gonna stick with 2 bars. Just gonna increase my bar size number 9. All right, and that is easy because number 9 is my favorite because it's easy, right? 1 inch square. So the provided now is 2 multiplied number 9 bars. All right, and this is 2 multiplied by 1 inch square, and this 2 inch squared is definitely bigger than the AS, which is 1.59. So easily satisfy my requirement. All right, so that's not bad, but troubles arrive since I over provided quite a bit. 2 compared to 1.59, that's quite a bit more than I wanted. So I had to redo my calculation. Okay, so check phi and mn again. What happens? What happens now, I turn this design problem to analysis problem. Turn design into analysis. Why? because I kind of provided bar already, isn't it? I already provided bars, and I have the geometry that is given. Geometry that is given, and this B equal to 12 inch, and the height is 24. And then I say I provide a number 9 bars and 2 of them at the bottom, 1 layer, okay? And even more specifically, I set the concrete cover between the center of this layer to the bottom here is 2.5 inch. So ds, in this case, because 1 layer also equal to dt, that is 24 minus 2.5 is 21.5 inch. So now the problem become analysis problem. All right, so how do we analyze this? Easy, right? Singly reinforced single layer. So A, compressive zone size equal to ASFY divided by a 0.85 F prime C B, and that is AS, which is 2 inch squared, and multiply FY, which is 60 KSI, and divided by 0.85, and F prime C is 4 KSI, and B is 12 inch. Okay, and so A now equal to 2.94 inch. Okay, that's my newly calculated effective compressive zone size. So now C equal to A divided by beta 1. And remember, beta 1 is what? 0.85 for 4 KSI. And this comes out to be 3.46 inch. Okay. So epsilon T, which is different than epsilon S. Okay. So this is last layer, right? This is last layer of steel, which in this case is same, 1 layer, but in other cases, be careful, okay? So dt minus C divided by C multiply epsilon Cu. And that is equal to 21.5 inch minus C 3.46 inch divided by 3.46 inch and multiply by 0.003 for concrete. So I got this number to be a 0.0156. When you see this number, you feel so happy if you're a true concrete designer because this is bigger than 0.005. And your old friend, tension control, jumped out and cheer with you, say, oh, you know what, tension control. Why is that so good? Because remember, in phi, we says, right, I have 0.02, 0.002, 0.005, and this is 0.65 and 0.9. Now we are far beyond this number, so we are eventually somewhere here. So we know for a fact that we have phi equal to 0.9. And this is consistent with our assumption to begin with. Okay, so with the happiness and joy I found with phi, so I can compute my final moment resistance or flexure strength ASFY equal to ds, or dt in this way is the same, minus half a. Bring the number, what is ASFY? I have 2 inch square, remember? 2 number 9 bar provided. Multiply 6 KSI and multiply by ds 21.5. And this A is this A right here, okay, updated. So 2.94 inch divided by 2, okay? So Mn eventually arrive at 200.3 kip foot. Okay, is this good enough? Is this good enough? Well, let's do a final check. Phi Mn equal to 0.9 multiplied by 200.3 kip foot. So that is approximately 180 kip foot, give or take. And that is definitely bigger than the applied moment, which is 145 kip foot. Okay, so we say okay, and we say design is adequate, and winner chicken dinner, right? So that's what we're dealing with. That's what we're dealing with. Is this done? Is this done? Somebody tell me, is this done? Are we happy? Are we good with it? Are we done? Not really. So 2 things we haven't checked yet, right? And I will leave it to next lecture. That is for the next step. This is step number 5. So it's next step, right? Check AS mean. Did your provided is bigger than AS mean or not? And also what step number 7, always the same thing. That is check your minimum beam width or spacing. Can you put your bars inside this 12-inch spacing you have for the section? Okay. Okay, so my time is run up, so we will pursue these two in Wednesday lecture. Okay. Now, all those of you who I said stay behind, please do. If you don't have that, you're free to leave, and I see you on Wednesday. Or if you have any questions, stay behind as well. Okay. Thank you very much.